We have a chair and we want to see how much force do we need to apply before it would just begin to tip back. Right, so normally, due to that spring at B, it's going to want to move, or it would want to stay horizontal. We start pushing on it and eventually it's going to tip back. Okay, so find the F to tip the chair. Again, the F that will cause it to just start to tip, because obviously we can push as hard. If we push as hard as we possibly could on it, it's going to go. So we want the minimum required for it to start to tip back. And we're given some information here that's going to be important. At B, we have a torsional spring, which we haven't seen yet. We've only seen linear so far. But torsional is going to behave much the same way. So torsional spring at B, so I will call that K theta for the torsional spring constant, 100 inch-pounds per radian. A torsional spring will apply a moment in a similar fashion to how a linear spring is going to apply a force. Right, so the stiffness, the torsional stiffness, 100 inch-pounds per radian, and it's pre-wound by 3/4 of a turn. I'll call that theta 0 is 3/4 of a turn, was 3/4 of a turn in radians, which will be more useful to us. Right, so if it's 3/4 of a turn, a full turn is going to be 2 pi radians. So 3/4 of a turn in radians will be 3/2 times pi. And that way everything will be in radians that we work with rather than in revolutions. This will be useful to us later. So that's all the extra information, and then we have the diagram also that we're going to want. But it's pre-wound by 3/4 of a turn, or 3/4 a turn, or 3/2 radians, and a stiffness of 100 inch-pounds per radian. Right, so we'll head to the free body diagram so we can find the force required to start to tip the chair. So what will the object be for our free body diagram where we're going to isolate from the rest of what it's connected to? What I do want to do is include the post in my free body diagram as part of it. Right, so as my object, I actually want the seat and the post. And you'll see why in a minute this is going to help. Again, beforehand, this doesn't necessarily make, it's not the most obvious thing to do, but we'll see later in the equation step that this will help us by including the post rather than separating the post. And this is where choosing that object gets more difficult. If I include the post, I now don't see the interaction between the post and the chair because they're still connected together in my picture. But what new forces do I see because now I've included the post as part of my object? Right, so at B, I have that torsional spring happening. So now I'm not including the spring in my picture, but I have to model what the spring does to the post. In this case, it's a torsional spring, so it's going to impart a moment on my post. So what direction should that moment be facing that the spring is imparting on the chair? Thinking here now about normally, how do we want the chair to behave? Right, and why should the spring force or spring moment be counterclockwise?
Still prevent the chair from falling back.
Right, so what's happening here is if we look at that little stopper at A, if we're exerting a counterclockwise moment, it would be rotating the chair forward into that stopper at A. So if it was going the other way, if it was imparting a moment in this direction, then it would want the chair to be rotating backwards, and that's, at least for this design, not what we want. So we know that that spring is turned in such a way, I'll call that C sub B, that it's imparting a moment counterclockwise at the post at point B. Right, it's connected to the, I don't know if they give it a name, right, the beam that holds up the rest of the chair. So kind of that stem of the chair. And we can see it has to be connected there because otherwise, can we just take this and move it left and right, move it up and down? That motion is restricted because it's pinned to that kind of base piece at B also. So at B, not only do we have a couple from the spring, but what else do we have happening there that's going to be affecting the post because they're pinned together? There's going to be some force preventing that motion in the X and some force in the Y also preventing that motion. And so because it's pinned, a BX and a BY, I'll presume are in the positive directions here. That little stopper at A, what is that going to do to the post? Right, there's going to be a normal force there because the post can't move to the left because the stopper prevents that. It could move to the right. The stopper isn't going to pull on it. It's only going to push on it. So right, we also have a force, I'll call it AX, from that stopper. That stopper is 2 inches from B, and it's 1 inch from the bottom of the seat. Right, so that stopper prevents it from moving to the left. We're assuming there's no friction until we get to the friction chapter later, so that stopper does not prevent it from moving up and down. And the stopper, it does allow it to rotate with respect to the stopper, so the stopper only exerts what must be a rightward force on the post. If we look at the free body diagram, we have this force F that we're to find. We have a moment CB, we have a force BX, BY from the pin, and we have a force AX from that stopper. So here we do have more than the usual 3 unknowns in the picture, but we will have ways of generating more equations here. So even though it looks like we have a lot, or we do have more than the 3, we'll have ways of finding them. If we stuck with just looking at the chair, we would not have ways of finding what was the post doing to the chair. So we will see the difference in that equation step in a minute here. But questions about the free body diagram. This one's certainly trickier than the free body diagrams we've been seeing so far. But the equation step just looks at the picture and sees what we have going on. So in the x direction, we have that applied force F. We have Bx. We have Ax, both of those point to the right. Three unknowns, nothing we can do with that at the moment. In picture in forces in the y direction, we'll have the weight of the person sitting on the chair, the negative 120. We have that upward force By from the pin. From equation 2, we can solve for By if we want. So By is going to be 120 since it's the only other vertical force. So that equation is used. We still have 3 unknowns and 1 equation, so we can generate another equation if we take the sum of moments around a point. Which point should we take the moment about, or is the most efficient to take the moment about here? Right, so usually the rule of thumb, it's not always the case, but if there's a pin in the problem, that point is usually the easiest to take the moment about. So there's that pin connection at B. So I'm going to take the moment around point B. So that means that Bx and By will not appear in this equation since they have their line of action pass through B. Kind of working away from point B, I will have that normal force Ax times its distance from point B is 2 inches. And according to my picture, it's going to be creating around point B a clockwise moment, so this will be a negative out in front. That's taken care of. Moving to the 120-pound force, that will create a moment around point B. Its perpendicular distance to point B is the 2 inches. And that 2 is going to create a clockwise or negative moment around point B. And finally, moving up, I have that force F. And its perpendicular distance to point B is going to be this vertical distance. It's a horizontal force, so I use the vertical distance. It's 14 to the bottom of the seat, plus another 3 inches below that to get to point B. So it's going to be 17 inches from point B. And in this case, that 2 is going to create a clockwise moment, so that also will be negative. Right, so all the forces are taken care of. What else do I need in my moment equation around point B? Right, the couple, the moment caused by that spring that's attached to at B. We know that that couple is going to be counterclockwise because we know that it's trying to rotate it forward instead of leaning it back. So I also have plus CB. The forces get multiplied by distances, the couples do not. It doesn't matter at what point I want to take the moment about, couples will always appear in this equation. So looking at equation 3, I have AX, I have F, I now have CB. So between equations 1 and 3, I don't yet have enough equations to solve for my unknowns. Equation 2 I've used up. So I have really 2 equations left, but I have 4 unknowns. AX, F, BX, and CB. Now I can use the information to have a spring, so I can use Hooke's law. For a torsional spring, it's basically the same idea. It's going to be the torsional, the moment caused by the spring will be the torsional spring constant times the angular deformation, which we can call theta here. This we were given in inch-pounds per radian, which means that the angle has to agree with that. So we were given that it has a spring constant of 100 inch-pounds per radian. And when the chair is vertical, that spring has been deformed 3/4 of a turn, or 3/2 pi radians, from where it usually wants to be. So that angular deformation is 3/2 pi. Again, radians and radians. So our result, the moment, will be measured in inch-pounds. So the couple we get 471 inch-pounds. I guess really that's a solve step. I've added a third equation for my 4 remaining unknowns. But again, looking at equation 3, I don't know AX or F. I still don't know BX either. AX, that normal force, the picture doesn't know that I'm looking at it when it's about to lean back. But if I'm looking at a situation where the chair is just about to start to lean back, that means that that contact force between the stem or the post and A, as soon as it loses contact, there's going to cease to be a force there because, again, it can only push on it, it can't pull on it. So if I'm looking at it just when it's about to break contact, now I can set that AX equal to 0. But this picture would still be true even as long as we're in equilibrium. It would still be true that the contact force I could find in AX, but only at the point it's just about to lose contact. That's when it's going to be set equal to 0. So that lets me put a 0 in here and a 0 in here. So that 5th equation, because we're just about to lean back, just about to lose contact, drops to 0. That provides that 4th equation for my unknowns. Now if I look at equation 3, I know the couple because I know how much torsion was in the spring. That AX dropped to 0 because I'm about to lose contact because I'm looking when it's just about to lean back. So the last thing I don't know is F, the force that causes it just about to lean back. So that force is going to be 13.6 pounds.